All right, good afternoon, everybody. I am Kimo from OpenAI's Threat Intelligence team, and this is Joseph from our Detections and Response team. And today we're going to talk to you about how we use AI to detect malicious activity on Mac devices. Here's what you can expect for our talk. First, I'm going to talk you through some of the background of how we use AI for different security purposes, and then how we set up the lab for this research. Then I'll give you some use cases to show you what the output of that looks like and how we can detect different types of malware and then other activity on Macs. Then I'm going to pass it over to Joseph, who will talk to you about how we can give additional information as context to AI models so you get more effective detections, and how to do prompt engineering so that you can better tell the models what you want it to do and how to do it. Then we'll wrap it up with some takeaways and some of the future research ideas that we have. So at OpenAI, we use our AI models for a lot of things, and that includes security use cases. And we do that so that we can reduce that human burden for doing the security engineering, and then also to increase our velocity of work. And when we get those projects into a certain state where we think it's going to be useful for other people, we like to go out and tell people about it so that they can incorporate it and advance our mission of making sure that everybody benefits from AI. So some specific examples: 2 weeks ago, my coworkers gave a presentation at CyberWarCon on this thing that we call Intel Assistant. And this is an agent that we built that automatically plans, executes, and then documents technical threat intelligence investigations. Earlier this year, some of our other coworkers gave a talk on how we've linked up our models to Slack chatbots so that we can triage, route, and then respond to common security questions in Slack. And then at DEF CON, our head of security sat down at a DARPA panel on the AI Cyber Challenge, where our models will be used to identify and then patch software vulnerabilities. So one of the questions that we had was, can we use these AI models in order to augment our detection strategy? So processes and commands are just language, right? They're words. And so it stands to reason that a large language model should be able to do some degree of recognition on that and assess that command line activity and surface malicious actions. And the TLDR for this talk is that yes, so we can use some LLMs to detect malicious activity. Those LLMs are going to perform better if you give them more context on what actually happened on the device. And those LLMs are going to perform better if you do some good prompt engineering and give it explicit instructions on what you want it to do and how it should do that. If you want to do a similar project, here's what our lab setup for this research looked like. We had 2 macOS VMs and then a couple of users to represent technical individual contributors, or ICs, managers, and then non-technical ICs. We used ESLogger to log those endpoint security framework events as a JSON file, and then used FileBeat to pull those logs in. We also had Elastic Agent running on that device, but we wanted the process group ID specifically, so that's why we used ESLogger as well. All of that information gets sent over to Logstash, then to Elasticsearch. Then we use a Jupyter Notebook to go query that information out of Elasticsearch, do a little bit of like massaging of how to format the text, and then send it over to the OpenAI API to get a analysis back. The type of activity that we're pulling from Elasticsearch are the processes that are running on those devices. So that includes benign activity, which we have a lot of, because most activity on computers is benign. And that includes things like users browsing the web with Chrome or checking their email, and then all of the background processes that just happen on a running laptop or other Mac device. And then there were some specific malicious activity types that we wanted to look for, which included info stealers, loaders, remote access tools, insider threats, ransomware, and then generic backdoors. And to drill in a little bit more, so this is what we're generating on the left-hand side. You got all those processes that are executing. We're going to pull those in. We're going to send those over to the AI model, and what we want to get back is like a structured object or a JSON that tells us which of these processes was bad, what host that process was found on, the suspicious score from a scale of 0 to 10, a verdict, which is like a binary, this is suspicious or this is benign, a set of MITRE tags that was found in the activity from those processes, and then finally like a paragraph of analysis. So now let's see what the output looks like. Let's start with info stealers, because they're so hot right now. Great talks yesterday from CrowdStrike and Huntress on like how that ecosystem has evolved on macOS. So we wanted to take a look at that. We tested it against a bunch of different info stealer families, but I wanted to like highlight this one. When this was found by Moonlock in August of this year, it was fully undetected on VirusTotal. When we ran it in our environment and then analyzed the output of it, we got the stuff that you see on the left-hand side. So you can see that our verdict was suspicious, had a score of 9 out of 10. And then we've got some MITRE tags for defense evasion, execution, and persistence. Now, I know the analysis has like a lot of stuff going on there, so we've highlighted some things that we think are pretty neat that the model found through those process command lines. So you see that there's multiple instances of base 64 encoded commands, which is commonly used to obfuscate malicious activities. We can see that it downloads a file from a specific C2 server. We've got removing extended attributes, which was called out as a thing on the Moonlock tweet. And all those things were done to bypass macOS security mechanisms. The other thing I want to note is that we use GPT-4o for that analysis, and the training knowledge cutoff is December of 2023. So there's no way that we had information about that malware sample in our training data set, which is good because that means that we can extrapolate from the training set into unknown malware and still correctly identify it. Next, we looked at a loader. So Group IB found this last month, and they attributed this activity to the DPRK group Lazarus. Executed again, fully undetected on virus total. We see it as suspicious with, again, a really high score of 9, and we can see execution and command and control, which we would expect to see from a loader malware, highlighting that it's using AppleScript to get a password from the user, and then curl to reach out to a C2, download a file, and I think it executed it again after that. Then we looked at remote access tools. This was to see how we perform against like some hands-on keyboard type of activity. For this, we used the MITRE Caldera platform. If you're not familiar with that, it's a threat emulation tool that uses a Golang-based agent to execute what they call abilities. An ability is just like a specific implementation of a TTP from the attack matrix. So the set of abilities that we gave these agents were like copy contents from the clipboard, record the microphone, go find, collect, and exfiltrate files, and enumerate the network. We ran it in a few different scenarios, one as a technical user, one as a non-technical user, as an unobfuscated binary that was called Sandcat, and then as an obfuscated binary called XPC proxy to see if we could trick the AI into thinking it's just a normal XPC proxy application. In all cases, we got a score of 9, verdict of suspicious. There's a little bit of variation in the tags that the model applied to it, but in general, it was command and control, collection, exfiltration, defense evasion. And then in the analysis, we can see that XPC proxy was connecting to a server, which looks like setting up a command and control connection. And then we've got some data collection activities, a bunch of base 64 decoding, piping to shell eval, which is pretty sus, and then curling to upload files. So that seems good as well. Next, we looked at some insider threats, and to do this, we had some scripts that would commonly be used by like an IT administrator to do things like create backups, check network connectivity, and then audit users in the Active Directory domain that our Macs were joined to. So on the right-hand side of this slide, you see the analysis when we ran it as an IT admin user, and it's benign with a score of 1, so completely expected for an admin to do those types of actions. On the left-hand side, you've got a non-technical user, and it's a slightly elevated score here of 3, but still classified as benign. So there's a little bit of like the black box that happens with the AI models, so we don't exactly know. But our thought was that this is a people manager, and in some instances, it's going to make sense for a people manager to audit who's in their organization, so maybe the AI thinks it's okay. So to test that a little bit more, we then ran it as a non-technical, non-manager user. So here it was a customer service representative, and we got a verdict of suspicious with a score of 7. So it's not the highest score that's possible, but it's still unusual for a customer service rep to run dscl and dsconfig.ad commands. And lastly, we looked at ransomware. And as you can see here, this is not a great approach to detect ransomware. It was labeled as benign with a score of 2. And I think it's more accurate to say that the AI is not good at detecting maliciousness when there's not enough context for it to figure out what actually happened on the device. So this not lockbit sample that we pulled down and ran has a single program called lckmac. It runs, it spawns no additional processes, it just encrypts all of your files. So didn't have enough information to say this is good or bad. We could probably have countered some of that by taking the file modification events, which would have represented the encryption of those files, and then sent all of that over to the AI to assess. I don't think that's a great strategy because we had 60,000 encrypted files made on our lab. So in a real device, that's probably going to be much higher. That's a lot of API calls to an AI model, so it's going to get expensive. You have to manage context, all this stuff. It's much better to have like a real AV or EDR on your device that's going to find and stop that encryption process as quickly as possible. So since since context is so important, I'm going to turn it over to Joseph to talk to you about how to add that context in.
Hey everybody, my name is Joseph. I work on detection and response at OpenAI. So we've experimented with several levers that affect the ability of our models to detect malicious behavior. And I'm going to talk about two of what we've found to be the most important factors. Those are context and the system prompt. So the first of features that we found to have a relationship to GPT detection quality is context, as Kimo mentioned. And we can think of context as the surrounding information that is related to the input data that we want GPT to analyze. So some context features include employee role, employee location, other commands executed from the same process that we're analyzing, and file creation and network connection events. The thought is that much like the way a human analyst will draw connections between data to analyze security events even more effectively, then GPT will also be able to use contextual information provided by us to deliver stronger judgments. So, to test this hypothesis, we process logs in the lab environment using 3 different architectures with increasing levels of context. So here we have detailed the first 2 implementations. The one on the left is isolated commands. This is pretty much the lowest level of context. So the way this implementation works is we take each process event and we have GPT analyze it one by one with a separate call to the model for each command. So here GPT doesn't know what commands came before or after the command that it's analyzing. The second architecture we took provides a little bit more context. It pulls commands and then rather than examining them in isolation, it groups them together based on the process group leader. So in this experiment, we grouped it that way. You could also group by time, by session ID, or something else. But the idea is to provide GPT with some contextual understanding, namely the fact that these commands are connected thematically by a particular process. And then also, GPT knows what commands are occurring before and after each other in chronological order. So we compared the performance of these 2 implementations by running around 8,000 commands through GPT and then normalizing the results based on the process group leader, so 2,500 unique processes. And we compared the performance between the grouped command approach and the isolated command approach. So we found that low context and high context have equivalent true positive detection rates, but that the less context you provide the model, the higher the false positive rate becomes. So here the isolated command approach has about 3x the false positive rate as the grouped command approach. And there's 2 reasons that we can explain this by. The first is the binaries that we ran in the environment run things like OSA scripts and other command activity that the model is just really good at detecting, so true positive rate is going to be high pretty much across the board. And the second is that we found that GPT generally leads more paranoid. So when you provide less context to it, it's going to be more likely to provide a suspicious rating in general, which is why this false positive rate is so high. And that's illustrated by the example we have on the left. So here we have this benign syslog command, but the low context GPT specifically calls out the fact that it just doesn't have enough information to know whether the command is suspicious or benign. It says if it's executed by a known and trusted administrator, then it's likely to be benign, but really I don't know, so I'm going to call it suspicious. So we thought about that and implemented a third architecture which takes into account the importance of having the user's role when analyzing security data. So this final architecture is like the second one in that it groups commands based on the process group leader, but prior to sending it to GPT for analysis, it enriches the process data with the role of the user. So the idea is that this should correct some of those low context false positives that are generated because GPT doesn't know whether it's a technical or non-technical user executing the command. So here we have a comparison of all 3 implementations side by side. And we found that the architectures with the highest context, especially the one that grouped commands and then enriched with role information, had significantly improved precision and recall. That is, they more effectively identified malicious behavior while maintaining a low false positive rate. There's a few explanations for this, and a few things we found that context helps GPT do better at. The first is assessing actor intent. So just like a human analyst, knowing the user's role and the wider sequence of commands executed in a given process group lets GPT calibrate its judgment a little bit more effectively. So for example, an Nmap scan might be detected as malicious in a vacuum, but if GPT knows the user's role as network engineer and the preceding commands are testing related, GPT might be more likely to rate that as a benign command. The second thing that more context makes GPT better at is handling obfuscation. So we found that GPT is much better at detecting tactics like masquerading files, live off the land, and chain encoding and decoding when it's able to see commands in sequence rather than in isolation. So we found that context is pretty important. And the other key feature, and probably the most important one that we've looked at, is the system prompt. So first, we're going to walk through how to develop a prompt like the one that we used in our experiments. And then we're going to evaluate just how important a rigorous system prompt is to the effectiveness of the model at detecting malicious behavior. So to create our prompt, we followed some pillars of a generally accepted prompt engineering wisdom. So there's a lot of guides out there. OpenAI has their own prompt engineering guide on our docs. And this one details 6 important steps to constructing a system prompt. So those are write clear instructions, provide reference text, split complex tasks into smaller subtasks, give the model time to think, and then test changes systematically. So we divide our prompt into sections for clarity to the model and maintainability. You'll see one of the sections for illustration below, instructions. And the first pillar that we try to adhere to is writing clear instructions. So there's 3 implications from this. The first is language should be clear and succinct. The second is it's important to be precise about the input the model will receive. So for example, if the prompt states that network data is going to be passed in, but then you pass in process like file execution events instead, the model might waste tokens reflecting on the absence of the data that you promised it. And then finally, the prompt needs to be consistent throughout. So if you do things like tell it to tag with MITRE in one section and then talk about the diamond model in another section, this can confuse the model and lead to more variable output. The second pillar is splitting complete tasks into simpler subtasks. So I have 2 sections of the prompt here that sort of illustrate this concept. That's tagging and output. And you'll see an example output right there at the top right of this malicious command. And the idea here is we break the analysis task up into tagging behavior, so with MITRE tags, into rating the suspiciousness of the command on a scale of 1 to 10. We have it generate a human-like short analysis explaining the logic. And then finally, we have the model provide this binary verdict of the command, which is either suspicious or benign. We've found that when you break the process up into disparate steps, rather than just, say, asking for like a text analysis or a binary judgment, this increases the model's accuracy. And the final pillar is giving the model time to think. So the idea here is you prompt the model in a way that mimics chain of thought behavior, which has generally been found to increase model performance on a range of evals. So here is another section, analysis section. And basically what we're doing here is telling the model to think through each command one by one, and then analyze it in the context of the previous commands that it's already analyzed in that API call. So we also have the model produce this human-like long-form analysis first, prior to generating the suspicious benign verdict. And this forces the model to think through its analysis. All right, so we've talked a lot about how we constructed our prompt, but how important is this? Will GPT without such a detailed prompt be potentially just as effective at detecting malicious behavior? Maybe the baseline security knowledge is really all you need. So to test this, we took this shortened version of our prompt that you'll see on the right, with just a few sentences of instructions and then an output. And we compared its performance analyzing around 2,500 process groups from our lab versus the implementation of the full prompt that we just detailed. And we found that, on average, the detailed prompt performs significantly more effectively than the abbreviated prompt. You'll see the curve and precision recall numbers on the right. So the detailed prompt has much higher precision, so a lower classification of false positives, and equivalent recall, so they both correctly identify malicious behavior at the same rate. But I'd say the advantage of a detailed prompt is really magnified once you deploy this kind of model in an enterprise setting, and then you can tailor your system prompt to the particularities of your organization, like expectations for specific roles and so forth. This takes us to the conclusion. So we have a few takeaways from the talk. The first, just to call back to those items that Kimo mentioned at the beginning. So we found that LLMs can detect malicious behavior on Macs. They're definitely a tool to augment your detection set. I wouldn't replace your EDR with them, but there are several advantages in adding LLM detections. The first is the fact that you can have a single detection engine, so a detailed system prompt and architecture that will scale to several attack types. So like Kimo showed, one prompt can detect multiple different kinds of malicious activity, info stealers, loaders, and insider threat, and that was all based off the one prompt that we just went through. The other reason why you might want to use LLM detections is that many endpoint detections are brittle. So we saw some talks from Huntress yesterday about the difficulty of detecting info stealers given the rate of development, and then earlier we saw a talk from Elastic's about the ease that actors evade detections. The benefit of LLM-driven detections is they're not dependent on the syntax of the input. You can't really evade them as easily by just using a different path or application or utility because they're not narrowly focused on a specific attack pattern, but rather they're generally looking at the semantic information passed in and generating a judgment. Some other takeaways that are pretty important from implementation is the question of what model to use. So we found that 4.0 is more effective than 4.0 mini. However, 4.0 mini is cheaper and achieves strong performance too. So it may be possible to string together multiple 4.0 mini models and incorporating what we talked about context, provide that context to 4.0 mini and render an equivalent output and therefore implement this more effectively. And then finally, prompting. So we found that a detailed system prompt is more effective and significantly improves performance. I definitely keep in mind, if you try to implement this, that even minor prompt changes cause the model's output to vary. So we'd recommend using some kind of version control and an eval system for prompt development. And then finally, keep track of new features. So functionality like GPT structured outputs help the model adhere to JSON schema consistently in the output. And this allows you to plug the GPT detections into other automation like a SIM or a SOAR easily and operationalize your GPT detection analysis.
Cool, and some things to look forward to in the future and future research ideas. So our models are going to continue to improve. That's kind of the point of the company, is to make those models perform better and then also reduce the cost of them. One of the things that I'm really hoping and looking forward to is a larger context window. Mandiant put out a blog post pretty recently about how they used their Gemini model with the 1 million context window. And with that, they were able to analyze a sample of malware, determine there's an encrypted section, write a decryptor for it, and then extract indicators out of that encrypted blob, all with AI, so that's pretty cool. Some other things are, we use the base 4.0 family of models for this. There is no fine-tuning. So we could look into doing fine-tuning to make that model perform better as a detection analyst / stock analyst. Retrieval augmented generation, or RAG, that's a way of getting additional context from relevant documents. So one of the cool things that we could do with this is maybe expose our GitHub repository as a vector store and then do retrieval against that. And that will let us suppress false positives for things that we develop that are uncommonly seen outside of our organization and make those things more specific to us. Using the search capabilities inside of our models would allow us to reach out to the internet and get some current context. So in one of those analyses, there was a URL. So imagine that the model's like, oh, a URL, let me go Google that and see if there's any reports documenting a new campaign using it. And then lastly, using the reasoning models. So O1 is better at the reasoning, the long-term tasks types of activities. So incorporating that into this type of flow, I think that'd be a great candidate for something like a response on the response side instead of on the detection side. And then finally, just applying this to other telemetry, we focused on those command line activities here. but we could do the same thing with application logs or network data. And I guess my one more thing. Okay. It's hard to see from over there. But so we did several different InfoStealer families, but we didn't do all of the InfoStealer families. So while I was sitting in the audience yesterday listening to those talks from CrowdStrike and Huntress, I was like, oh, I hadn't heard of that one before. Let me go find a sample and go run it and see what happens. So that's what I did. And here we've got the cuckoo result that I think Alden was talking about. And so I downloaded it. What you don't see is like me running it in the VM and all the other stuff that's happening in the background. But here's just us pulling it based off the process group leader that I noted from when it executed, getting the results from Elastic, merging it with our user information so that we enrich it with who's running it, and then sending it over to a little function that formats all of those commands into like a markdown table and then passes it over to the model. And then here's the result from it. And we got suspicious, 9, some of the things that we see here, removing the quarantine attribute. We've got OSA script to go get a password. We've got copying Safari cookies, history, bookmarks, keychain, and notes to a temporary directory. Launch CTL to do persistence as my Mac video converter. And then we did a Banshee talk while CrowdStrike, or I might have it backwards. But anyway, we then did a Banshee sample, and same thing, suspicious, score of 9. And here we can see that it's got OSA script getting another password. We've got those system profiling commands with system profiler and SWVers. We got the curl. Oh, this was the Huntress one. And then the URI that they mentioned, where they're always seeing this pattern on their URLs. We got the ditto. And, oh, actually, I forgot one up here. Sorry. Here's the muting the system volume to avoid those alerts and notifications. So all of that just from taking the commands that are executed, throwing them over to ChatGPT, and asking it to take a look. And yeah, thanks for sticking around for that.